All right, so it is 3:30. We can go ahead and get started. It is 3:30. We can go ahead and get started. Just give me 1 second, set something up here. All right, cool. What we have coming up in class, our homework assignment 2 is going to be due tomorrow on Friday, just like all of our homework assignments. So again, if you have any last minute questions that you'd like to ask, I do have my office hours on Friday, so feel free to stop by and ask me any questions that you'd like. Also, Piazza is available as well if you're, not able to, drop by office hours or you'd like to, get those questions answered a little bit more quickly. So what we're going to do today is hopefully finish up with this Unit 3 discussion, where we're talking about various different types of ways in which we can evaluate or answer questions about a particular clustering that we have created for a given data set. So one of the techniques or one of the types of clustering evaluation metrics that we've discussed is what we call unsupervised clustering evaluation metrics. Now, these evaluation metrics get much more to the heart of essentially what it is that we are trying to do when we create an ideal clustering. So again, when we're creating an ideal clustering, generally speaking, our overarching goal is to create some sort of groupings of observations in which the similarity of the observations within a given cluster is very high, if you will. Or in other words, we have a high amount of cohesion within the cluster. And in addition, our goal is also to achieve clusters in which there's a high amount of dissimilarity between the observations in two distinct clusters. In other words, we are trying to maximize what we called the separation between two or more clusters. So we discussed that there's a variety of different ways in which we might go about measuring cohesion and separation of a given clustering or the clusters within a clustering. And so one of those techniques is to use what we call graph-based definitions of separation and cohesion. And this is all based on using, what we call a proximity matrix, which involves, calculating some sort of distance metric between all pairs of observations in the data set. And generally speaking, we'd like for that proximity to be as, close as possible for observations within a given cluster. And we'd like for that proximity to be as, basically dissimilar as possible for observations in different clusters. So one specific type of graph-based definition of cohesion and separation is utilizing what we call the silhouette score. So you want to remember we calculate the silhouette score of each observation in a data set for a given clustering of that data set. But we can basically aggregate and examine each of those individual silhouette scores to also learn more about the overall cohesion and separation of, each of the clusters in a given data set or of a given clustering, as well as the overall clustering of the data set. So basically, we introduced the equation for how we go about calculating the silhouette score of a given observation in a given clustered data set. But we didn't actually get to the part in which we describe essentially how do we interpret these these silhouette scores. Now, what we did discuss is that the silhouette score for a given observation is always going to range between -1 and 1. So by approximating ourselves what the silhouette score for each of these three circled points is, we hope to gain some intuition, if you will, as to what these silhouette scores are actually calculating for, so what these distinct values mean. So what I want you to do is I will open up the breakout rooms in just a second. So yeah, basically use the silhouette score equation, so these three equations here, to roughly approximate what these three silhouette scores would be for each of these three distinct points. So talk about that with the people in your group, and then we'll meet back and discuss. Okay, so I'm going to open up the breakout rooms, and again, try to select a room with about 4 people. And again, in the interest of time, I'm just going to start randomly assigning people. But again, you can change your group. Right. So everybody is assigned to a breakout room. So if you could go there now. right, so welcome back. So I'll give people a few more seconds to come back to the main room. And yeah, so hopefully you were able to discuss some rough approximations for what these 3 points silhouette scores might be. So just to kind of aggregate what we were discussing in the breakout rooms, we just opened up a Zoom poll. So of the orange, green, and blue points, which point do we think is going to have the lowest silhouette score? So 1, 2, or 3? Okay, so try to submit in the next few seconds, and we will discuss. All right, shut down the poll now. All right, looks like we are about at an even split between the orange point and the blue point. So actually, if we come up with a rough approximation, if we were to actually calculate the silhouette score for each of these 3 points, what we're going to see is that the blue point ends up having the lowest silhouette score. And also take note that this blue point looks like it actually is, in fact, what we call a straddle node, in that it straddles multiple clusters, or it's this point technically assigned to cluster 2, but it's actually quite close to the observations in cluster 1. So let's go through each of these 3 points one by one, approximating the AI, the BI, and the SI for each point. So let's start with the orange point. So you want to remember the AI in your silhouette score calculation is the average point, or excuse me, the average distance that this point is from all of the observations in the cluster that it was assigned to. So that would be the average of all these distances here. So that would approximately give you like an AI value of something like this. And then to calculate the BI, what we're going to do is first calculate the average distance of that point to all other points in this cluster. So that would be roughly some average distance of something like this. And then we're going to do the same thing for the other cluster. So calculate the average distance at that point to all the observations in this cluster. And that would give you something, an average distance of like this. And so the BI is the minimum of these two average distances, basically to all of the clusters that it's not assigned to. So I think the smallest of these two average distances would be roughly this one. And so this is going to be my BI. So what we can see here for this orange point is that the AI is comparatively a lot smaller than the BI. So therefore, when we normalize by the maximum of the AI and the BI, that maximum is going to be the BI. So therefore, what that means is comparatively, this is going to be a relatively larger distance, or the distinction between the BI and the AI is going to be a lot larger. So what that means is that your SI is going to be quite large as well. It's going to get closer to 1, essentially. And this makes sense because basically we can see that this AI is very well settled within the cluster that it was actually assigned to. It's not close at all to, observations in some other cluster. And so we can do the same thing. We're actually going to see the same relationship for this green observation as well. So to calculate or roughly approximate its AI value, again, what we would do is we would find the average distance that point is from all the observations in the cluster that it was assigned to. So that might be a distance something like this. And then to calculate the BI, what we do is we calculate the average distance that point is from all observations in cluster 1. That would be a distance of something like this. And then we calculate the average distance of this point to all observations in this cluster. That would roughly give you like a distance of something like this. So I'd say that this distance is roughly the smaller one. So that means my BI would be approximately a distance of something like this. And so again, we can see that in this case, the BI is comparatively a lot larger to the AI. So because of that, when we calculate our silhouette score for that green point, that silhouette score is also going to be a lot higher. Or in other words, it's going to approach 1. Now this is going to contrast with what we approximate our silhouette score for the blue point to be. So again, what we would do is find or approximate the average distance of this point to all the observations in the cluster that it was assigned to. That would be about distance of something like this. That would be my AI. And then to calculate the BI, I would find the average distance of all points in this cluster. That would be an average distance of something like this. And I would find the average distance of the blue point to all points in this cluster. So that would be a distance of something like this. So the smaller of these two average distances is this one here. So my BI would be approximately a distance like this. And now what we can see is that my AI and my BI for the blue point are actually approximately very close to each other. So maybe the BI is even smaller than the AI. It's kind of hard to see. So they're very close. So what that means is that my SI for the blue point is going to be approximately some value that is close to 0. Okay. And so using this intuition in mind, this is basically how we go about interpreting what a silhouette score means. So actually, if we were to calculate the silhouette score for all of the points in the data set, this is what we would actually end up getting. I'll just zoom in really quickly here. So we can see that the silhouette score for observations that exist basically on the border, or basically that straddle multiple clusters here, actually do end up having the smallest silhouette scores, whereas the observations, which are relatively far away from a cluster that it was not assigned to, end up having much higher silhouette score values. Okay, so that's exactly how we end up interpreting the individual silhouette score. So we say that for a given observation, xi, that has been assigned to a given cluster in a data set, we say when the silhouette score of that object is large, what that means is the object is closer to objects in the cluster that it is assigned to than objects in different clusters. And similarly, when the silhouette score of a given observation is close to 0, roughly what that means is the object is about equally close to objects in the cluster that it is assigned to objects in some other cluster that it was not assigned to. And finally, the worst case scenario is, I'll say, all right, I want to specify larger and positive. So the final scenario is when your silhouette score of a given object is larger and negative, so closer to -1. What that implies is that the object is actually further away from the objects in the cluster that it was assigned to, and it's actually closer to the observations in some other cluster that it was not assigned to. The ideal scenario is one in which all of your silhouette scores are exactly 1. Or in other words, it's as close as possible to the observations in the cluster that it was assigned to, and it's as far away as possible from the observations in clusters that it was not assigned to. Yeah, so someone's asking me a direct question. Is the BI minus AI always positive? Yes, and kind of, yeah. So we just got to that. So technically, yeah, it is entirely possible for the BI minus the AI to be negative. And again, that would be a scenario in which your observation is actually closer to observations in the cluster that it was not assigned to, indicating poor cohesion and poor separation. Okay. Great, good job. So any questions on that? All right, so again, this is how we evaluate the cohesion and separation of an individual observation. And like we discussed on Tuesday, you can compile all of the silhouette scores for each observation in the data set and basically put it into a sorted bar plot, also known as a silhouette plot, to learn more about the overall clustering of the data set, as well as examine the overall amount of cohesion and separation for each of the clusters within that clustering. So for instance, this silhouette plot here is actually the silhouette plot that you would get if you were to take this or these two clusters here, calculate the silhouette score, specifically using the distance metric, or excuse me, the Euclidean distance to measure distance between 2 points. And this is what you would get. So again, you want to remember that each of the silhouette scores are grouped by the cluster that they were assigned to, and they are sorted in descending order within each of those groups. Okay. Now, what we can see here is that, even though this clustering of these two clusters here actually did a good job based on what we can see with our eyes, the face value interpretation of this silhouette plot would actually suggest that this is actually not a good cluster, right? Because we can see that both of these clusters here, cluster 0 and cluster 1, have a lot of negative silhouette scores. So what that implies, and we can also, we can see that here, is that there, are some observations like this point here, which are in fact a lot closer to observations in a cluster that it was not assigned to, thereby at face value suggesting that this is not a good cluster. But like we said, the Euclidean distance metric, as we've seen with this data set, many, many times, the Euclidean distance metric is actually not going to be the most useful distance metric to use to evaluate clusterings for a data set such as this, or to basically, even detect the clusterings within a data set such as this. So now, for instance, if we were looking at a data set such as this, where we have 4 overlapping points in each of these 4 clusters that we identified here, if we were using the distance, the Euclidean distance in this case, then what we would actually see is that the silhouette plot generated by each of the silhouette scores of this clustering and this data set actually produces the ideal scenario in which every single silhouette score of each observation is exactly equal to 1, representing that it's as close as it can be to the observations in the cluster that it was assigned to, and it's as far away as it can be from observations in a different cluster. Now, more often than not, you're never going to see like silhouette plots that look, this perfect. But ideally, like the closer those values are to 1, the better. And so basically what a silhouette plot allows for us to do is to evaluate the cohesion and the separation of each of the clusters individually. So we can see, for instance, that all 4 clusters have perfect separation and cohesion in this very ideal scenario. So the silhouette plot allows for us to evaluate cohesion and separation of each of the clusters independently. However, if we're looking for simply just a single summary statistic to evaluate the overall cohesion and separation of an entire cluster ring, then all we have to do is simply just calculate the average of each of those individual silhouette scores of each point in the data set. So because each individual silhouette score can range between -1 and 1, what that means is the average silhouette score, naturally, also can range between -1 and 1. And so specifically, if you get an average silhouette score of 1, then what that means is, you might guess, the clustering has perfect cohesion and separation. I'm going to put a big caveat here. Based on the based on the distance metric that you are using to measure observation distances. Okay. And naturally, if you get an average silhouette score that is -1, then what we might guess as interpreting is that basically, yeah, this means that this corresponding clustering has the worst cohesion based on the particular distance metric that you're using. Okay. All right. Any questions on that? Okay. Now, again, I want to, circle back to how important the particular distance metric is when it comes to actually trusting that your silhouette score is going to be a useful metric for evaluating the overall cohesion and separation of the clustering. So, for instance, we can actually see, again, that this particular clustering of this particular data set actually did great. Right? It identified the 2 clusters that we can see with our eyes, we actually wanted to identify. But again, if you simply just used the Euclidean distance to measure the distance between 2 points, the corresponding, silhouette plots, as well as the corresponding average silhouette score of the clustering, would suggest otherwise to you. It would suggest that this is actually a very poor clustering of a given data set. But the thing here is, as we've seen before, the Euclidean distance is actually not usually the best when it comes to identifying and evaluating clusters such as this. But what we did see in a previous unit was that if we chose to define proximity, or distance, if you will, in a different way, we actually get much more useful definitions when it comes to identifying and evaluating clusters such as this. So for instance, we can use a connected graph-based definition to help us, more effectively identify, the high amount of cohesion and separation that we're seeing with our eyes. So for instance, we might instead to, determine or say that 2 observations in this data set are, similar. We might choose to measure the distance between 2 objects by first, again, defining this notion of connected, right? So we say that 2 objects are connected if they are within a distance of 0.5 of each other. And then we might choose to define distance in this particular case as one in which, 2 objects have a distance of 1 if they can be joined in a connected path. And otherwise, they have a distance of 0 if they cannot be joined in a connected path. So in this case, using this particular notion of distance, what we end up getting is, actually, I might actually switch this around, but let's switch this around to actually have, let's turn this to a 0 and this to 1, because it's actually a little bit more effective, because we want this to be a similarity-based proximity measure. So actually all of these values would have a distance of 0. And then all of these values would have a distance of 1. Okay, so basically what we're going to see here, if we're to use these distance metrics, our BIs would be a lot higher than our AIs for each of these observations. So by using this notion of distance, we would actually get 2 silhouette plots that looked like this, where basically every observation had a perfect silhouette score of 1. Okay. Now this makes things really tricky for us though, right? Because it's like, this is a very unrealistic scenario. we can't actually see what this data set looks like with our eyes, usually because we're usually dealing with high dimensional data. So this makes the task of, not just identifying the most appropriate clustering algorithm to use for a given data set, but it also makes the task of even evaluating how well your given clustering algorithm did all the much more difficult, because it's like we have to kind of know ahead of time, or we have to have a sense as to what the data set actually looks like, like what the shapes are, in order to even effectively evaluate how well our clustering algorithm did. So this has a lot of confusion to how do we know that we're actually doing a good job, essentially. So next week, we're going to introduce the TS&E plot, which is going to help us get a sense as to the shapes of the underlying clusters that exist in this data set. So a TS&E plot is actually going to help us determine if we're dealing with these, for instance, nested convex types of clusters, and therefore give us a sense as to perhaps A, what is a better clustering algorithm to use, and B, what is a better clustering evaluation metric to use. So I'm seeing a question here that says, wasn't there also a silhouette score of like 1.2 in that orange, blue, green example? Technically not. So yeah, so yeah. Now, while technically the legend does go up to a value of 1.2, just in terms of how it's choosing to create the buckets for the color coding. Technically, the actual numbers for each of these silhouette scores are not going to actually go above 1. So it's basically just what this is signifying here basically is that like all observations that are like between 0.8 and 1.2 are going to be given this color essentially. But yeah, the observations themselves don't go above 1. Yeah, so that's a good question. All right, any other questions about silhouette scores? Okay. So I think in the interest of time, I might skip over this for now. I think I'll come back to it if I do have some time. But yeah, basically what you want to remember is that the silhouette score of a given observation is, again, a graph-based, or based on a graph-based notion of cohesion and separation. But much like we saw, in Unit 2, in which we have many different definitions or types or ways in which we can define a cluster, there's many other ways in which we can define, the cohesion and separation of a cluster. So if we have time, we'll talk about, another way to define cohesion and separation. This is going to be based on, the notion of a prototype, which is going to be very similar to how we define, our prototype-based clusters in Unit 2. We'll come back to this a little bit later. So I think what I'd like to do next is kind of move on to another question that we often ask ourselves about, or when it comes to choosing the most appropriate clustering of a given data set. So let's just say we've settled upon a particular algorithm that we'd like to use. Now, often when we settled on that particular algorithm, the next question that we want to ask ourselves is, what is the best set of parameters to use for that given algorithm? So all the algorithms that we've discussed so far, basically the only parameter that we need to select ahead of time is simply just the number of clusters that exist in the data set. So pretty much the only way that we've discussed so far that allows for us to select, what is or to attempt to answer the question is, how many actual clusters exist in the data set, is simply just using the elbow plot methods. So again, elbow plot method also gives us indications about, whether or not the data set is clusterable. But as we saw in the beginning of this unit, the elbow plot method has its drawbacks because it is a algorithm-dependent way of going about looking for clusters. So similarly, if we want to look for how many clusters might exist in the data set, we could use the k-means elbow plot, which says basically when determining how many clusters not inherently exist in the data set, but how many clusters k-means can detect, we use, naturally, a k-means elbow plot, which plots the inertia of the clusterings found by a given clustering algorithm, by the k-means clustering algorithm. And generally speaking, where you see the elbow is roughly equal to how many clusters k-means can detect. Okay. And similarly, maybe we didn't trust k-means. Maybe we felt that, k-means is not identifying all of the clusters that might exist. So maybe instead, or maybe, in addition, we might choose to use k-metoids elbow plot. So we say when determining how many clusters k-metoids can detect, then we can use a k-metoids elbow plot, which again plots the objective function that we are ultimately trying to minimize, minimize with the k-metoids optimization problem. That is the distance of all points to their assigned cluster metoid. And again, you see an elbow in the plot. And speaking, where you see the elbow is unfortunately only just a suggestion as to how many clusters k-metoids can detect. Okay, and again, we don't need to bound ourselves to, either just using k-means or k-metoids to identify the number of clusters. We can actually just use any clustering algorithm that allows for us to specify the number of clusters in the data set. So we might simply just say, when determining how many clusters can be detected by a particular clustering algorithm that allows us to select the number of clusters, then we can use the corresponding elbow plot that plots the objective function value that we're seeking to minimize for that corresponding, I'll just say the objective function value that we're seeking to minimize of the clusterings found by that particular clustering algorithm. And again, if you see an elbow, what this suggests is wherever you see that elbow is how many clusters that particular algorithm can detect. Okay. And so again, just like we saw when using the elbow plot method to detect clusterability of a given data set, we're also going to see that the elbow plot method is unfortunately algorithm dependent. It can only detect clusters that that particular algorithm is designed to detect. Okay. So given that, given the fact that we probably don't want to literally just use every clustering algorithm that exists in the literature, right? And then create a corresponding elbow plot for each of those clustering algorithms, it benefits us to also explore clustering evaluation metrics that can, help us determine the ideal number of clusters that exist in a given data set that, again, are not dependent on any one particular clustering algorithm. So one such metric that we can reference is using our notion of what creates a good clustering based on, the assumptions of the average silhouette score. So like we said, if we assume that the particular way in which we're calculating the silhouette score, the average silhouette score, is effective for evaluating the cohesion and separation of a given clustering, then what we can do is create what we call a average silhouette score plot, much in the same way that we create a k-means elbow plot. So for instance, let's just say we decided, that we wanted to use k-means clustering, as well as, perhaps many other clustering algorithms as well. And so let's just say we clustered the data set with k-means, into a clustering with 2 clusters, 3 clusters, 4 clusters, so on and so forth. And for each of these clusterings, we plotted the resulting average silhouette score. So another way of going about evaluating whether, we selected the most appropriate or the best number of, clusters for that given algorithm is instead to choose the clustering and the particular cluster number that produces the, in this case, highest average silhouette score. So what that might suggest is that at the very least for that particular clustering algorithm, that cluster number is going to produce the clustering with the overall best cohesion and separation of the given data set. Okay. Any questions on that? All right, so we're going to look at a example in Python in just a second, but I want to touch upon a nuanced point here. So I never want you to think that, there's any one particular metric which is going to be able to effectively tell you the right answer in every particular scenario. So it's always a good idea, basically, to cross-reference multiple evaluation metrics to help you determine if this particular clustering that you're looking at is the one in which that best meets your particular research goals. So let's look at an example of what I might mean by that. So let's just say, for instance, we cluster this data set here into the 2 corresponding clusters. And so you can approximate this yourself, but roughly, generally speaking, the average silhouette score of this clustering is going to be about 0.5. So let's think about how we might actually go about interpreting that particular average silhouette score of the given clustering. So let's think about this interpretation here. So I take that 0.5, which is, about halfway between 0 and 1. And I claim that this silhouette score, this average silhouette score, implies that k-means, when we're looking for 2 clusters, it didn't perform great when it came to clustering this data set, but its performance was average. So what do we think? Is that an appropriate interpretation of that 0.5 value? And if you have an opinion, start writing up your answer in the chat as to why you think it is or is not an appropriate interpretation. All right, so I'm seeing a slight, or definite majority for false. So what's wrong with this interpretation here? Yeah, so someone's saying, I feel like a lot of data sets aren't perfect. Yeah, I mean, so basically if we were if we take a look at these 2 actual clusters that inherently exist in the data set here, these 2 clusters are not well separated at all. So if we were expecting to find, any clustering of this data set into 2 that produced a average silhouette score of, something very close to 1, then unfortunately we're going to be very disappointed. So basically, no matter what clustering you create of this particular data set, because these 2 clusters are so close to each other, you're actually not going to get a average silhouette score that's in any way, shape, or form close to 1. Now, the thing here is if these 2 clusters were much further apart from each other, then yeah, you should actually be expecting to find a average silhouette score of a particular clustering that you found that is in fact closer to 1. So basically the way in which, the maximum average silhouette score that you might end up getting is going to be very dependent on the nature of the data set itself. So again, you want to be careful about how you compare the average silhouette score found by clusterings for different data sets. So what I might say is, given that these, so given that the two, inherent slash actual clusters that exist in this data set are so close, expecting a clustering of this data set that gives you a average silhouette score that is close to 1 is unrealistic. Okay. Okay. So I'm seeing a question here. 0 would be the average slash insignificant, but 0.5 means there was still a difference between intracluster and intercluster distance. Yeah, so that's right. So basically, if you have a average silhouette score of 0.5, generally speaking, what that means is that on average, each point is about twice as close to the observations in the cluster that it was assigned to than the observations in the other cluster, essentially, which is not bad, if you will. But yeah, basically, like if if these clusters were a lot further away, then you could expect, for instance, that the average distance of point is from a cluster, the average distance of point is from observations in the cluster that it was assigned to is, 10 times as close to observations in another cluster, which is, technically even better. But, given that this was the data set that we were working with, an average silhouette score of 0.5 was actually pretty good comparatively. Okay. So again, having a sense as to, for instance, how well separated your inherent clusters are also is going to, inform how you should go about interpreting your, your clustering evaluation metrics, such as the average silhouette score. So again, having a sense ahead of time as to how well separated your clusters are is going to, help you more effectively evaluate how good your clustering algorithm is. But again, this makes things very complicated, right? Because again, we can't see these two inherent clusters with our eyes because this is a high dimensional data set. So we need to be thinking about, well, how do we know ahead of time how well separated our clusters are? So again, that's going to be a question that we're going to answer as we move on to subsequent units, essentially. But you want to be thinking about these complications here up front. Okay. All right, so just wrapping up with a couple of things we've sort of already said before, with average silhouette score. Again, in order for the average silhouette score to be an effective measure of cohesion and separation of a given clustering, you want to make sure that you're using a distance metric that is appropriate for the clusters that you're actually dealing with. So again, one more time, Euclidean distance is not effective for these clusters here. And so what is it about these clusters, or the nature of these clusters, that makes the Euclidean distance not very effective for a lot of the algorithms and evaluation metrics that we are using? So one of the key issues that these particular cluster shapes have is that they are not shapes that are what we call convex. So a convex shape basically represents a region, or any type of region, in which for any 2 points that you select within the region, every point in the line that connects those 2 points is also contained within that region. So for instance, just out of curiosity, do people know what these are? I don't know the extent to which, I don't know if Lucky Charms is a popular cereal in all places, but in the US and many other places, we have a very highly sugary processed cereal called Lucky Charms. And you have these little marshmallows that take on these shapes here. So for instance, let's take a look at this horseshoe shape. It's a lucky charm. So for instance, I can see that this is actually not a convex shape because there exist 2 points in the shape such that when I draw a line between these 2 points, there are points in that line that are not within the shape. So Zoom poll for you guys. Do we think that any of the Lucky Charms shapes are convex? So yes or no? Give me a few more seconds. Okay. Okay, so I'm seeing a majority of responses for no. And yeah, actually, I was very pleased to determine that none of the Lucky Charms are actually convex shapes. And I love using this whenever I talk about convex shapes. So yeah, basically you can see for every single one of these shapes here, there exist 2 points such that when you draw a line between the 2 points, at least one part of that line will go outside of the shape. Yeah, exactly. So the balloon looks kind of close to convex, but not quite. So if you draw like these 2 points here, the line goes outside of the shape. Okay, so the reason for this whole tangent basically was, yeah, if you plan on using the Euclidean distance metric to measure the distance between 2 points when you're calculating the silhouette score, then unfortunately, clusters that are non-convex in shape don't tend to work as well for this clustering evaluation metric. Or in other words, your silhouette scores, your silhouette plots, and your average silhouette score are going to be much less effective at, determining or evaluating the amount of cohesion and separation within the given clustering. But the benefit of using that average silhouette score to select the number of clusters is that you do not have to assume that you are using any one particular clustering algorithm to measure clustering performance. So again, the average silhouette score is not determining, how well, it's not determining clusters that k-means can detect, because what you could do is you could actually cluster this data set with other clustering algorithms. And you can simply just pick the average silhouette score that is highest to basically determine, what number of clusters you're looking for. The bullet point is average silhouette score is not bound to any one particular definition of what a cluster looks like, essentially. So that can be beneficial. So given, that there are always a set of assumptions that you need to be thinking about when, defining what a cluster actually is and what, makes for a good clustering, it's always a good idea to consult multiple methods and realize that it actually might be the case that there is actually not necessarily one right answer, the overall best clustering of your data set. But more so, you want to make sure, your ultimate goal here is to, number one, pick a clustering that best helps you meet your research goals. So we'll talk more about that a little bit later. But number two, you want to simply just make sure that you are understanding as much as you can about what's going on in this high dimensional data set. So the bullet point is you never want to select a clustering that would lead to somebody being misled about the nature of the data set. But again, this is why we want to consult multiple methods, because multiple clustering algorithms and multiple evaluation metrics can reveal different elements of what's going on in this high dimensional data set. Okay. All right. Okay, so running out of time. So let's move to the application. So we're gonna go back to that data set that we were exploring at the beginning of the unit. So So again, the data set that we're exploring here is comprised of 5 numerical attributes, which tell us something about a corresponding auction held on eBay. Now, in addition, we want to remember that there's this additional set of pre-assigned class labels, which we're not actually going to include in the clustering itself. So basically, when we run k-means, we're temporarily we're going to put it aside. But basically, after we've run k-means, we'd like to compare the k-means cluster labels that we created when clustering these 5 numerical variables. And we'd like to compare it to this set of pre-assigned class labels. So our overall goal here in this particular analysis is to simply answer a question. Is there an association between the clustering structure of this data set and whether or not the auction was normal or abnormal? Or in other words, whether there was no shill bidding or shill bidding involved. Okay, so we're simply just focusing on unsupervised clustering evaluation metrics now. So we'll put those pre-assigned class labels away for the moment. So what I'd like to do is first, I think we'll skip over this here, but basically, it's always a good idea to quickly describe the summary statistics that you can calculate for each of your numerical variables in your data set before performing cluster analysis, because this can basically give us a sense as to whether we need to perform some additional pre-processing of our data in order to get the kind of clustering results that we're essentially looking for. So we're going to explore this question more in our homework assignment, but something that you want to be focusing on in particular when you explore the summary statistics of your data set initially is, in particular, the standard deviation of each of your numerical variables. So in next Friday's homework assignment, we're going to talk about how to scale the variables in our data set and under what circumstances we might want to do that. But the bullet point is we want to think about, what happens, for instance, if the scale or the standard deviation of some of our variables is much larger than other variables. Is that going to give us the kind of clustering results that we want? So we'll think about that in the homework assignment. Now, it's also a good idea to, for instance, given that we have this set of pre-assigned class labels, it might also be a good idea to, for instance, explore how these pre-assigned class labels simply just relate to, what we can see with our eyes. So for instance, like all pairs of numerical variable relationships. So again, we can look at every possible scatter plot that we might make for each of our numerical variables by using the pair plot function. And if we want to color code by the pre-assigned class labels, we can specify the hue parameter and set that to class. Okay, so let's skip over some of this stuff here. And again, excuse me, because I want to simply just focus on clustering just my X data frame, I'm going to, for now, create a new data frame in which I have just dropped the class attribute for my full data frame here. And so these are going to be the variables that I will cluster, as well as determine if there exists a clustering structure within this data set. Okay, so let's go back to the Hopkins statistic, because again, before running any type of cluster analysis, you first want to make sure that, clustering the data set is a good idea. Or in other words, there exists some sort of, separation within a set of points here. So because the Hopkins statistic is non-deterministic, we're actually going to calculate 5 Hopkins statistics and evaluate basically all of them. So what I'm going to do is create a list or an empty list of Hopkins stats. And what I will do is simply just create a for loop ranging from 0 to 5, in which first, now technically I'm being a little bit a little bit sloppy and redundant with my code here. Could have actually done this ahead of time before I entered in the for loop. But regardless, I want to come up with that, the best or a good rule of thumb for the number of random points that I will be selecting when I calculate that Hopkins statistic. So what I'm doing here is I'm first calculating the number of rows in my X data frame, and then I'm calculating 10% of those number of rows, and I'm rounding it to the nearest integer. So if I want to quickly calculate a Hopkins statistic, I can use the Hopkins function, which unfortunately is not a function that is contained in scikit-learn. So if you want to install a package that will automatically calculate that Hopkins statistic for you, you'll need to run pip install pycluster-tend in your Anaconda command prompt to basically give you this Hopkins function here. Okay, so once you've done that, you can use that Hopkins function. And so basically the two inputs are simply just the data set that you'd like to evaluate whether or not it's clusterable, and P, the number of random points that you're selecting from the data set, and the number of random points that you're artificially generating within the range of values of the data set. Okay, and so what I'm going to do is I will calculate 5 Hopkins statistics, and for each of those statistics that I calculate, I'm going to append it to my Hopkins stat list. And so this is my list of Hopkins statistics that I have calculated here. So I might have given it away, but based on these Hopkins statistics that we're looking at here, do we think, that the data set is clusterable? So yes or no? Okay. So I feel like this is like one of those sort of redundant teacher questions where it's like the answer, the answer if you're not, if you're looking ahead is already here. But it's what this does suggest is that this is in fact a clusterable data set, that there does exist some sort of gapping or empty space within the range of points. And again, essentially what we're seeing here is that on average, these Hopkins statistics are much closer to 0 than they are 2.5. So what this suggests is that the data set is clusterable, at the very least, based on this assumption of the Hopkins statistic, in that there exist these gaps within the range of points in your data set. Now, whether that's a correct assumption or not, we don't yet know, but something to think about. Okay, so I've been talking a lot. Any questions so far? All right, so let's again just create, for starters, just a naive clustering of k-means. So let's just say we haven't done any parameter tuning yet. So let's just say, for instance, we've decided to explore a k-means clustering with 3 clusters. And so what we do here, as we've seen before, is we're going to cluster our data set into 2 clusters. We're going to set a random state for reproducibility. And again, this creates my k-means function. And I'm going to extract my corresponding cluster labels for each of the observations in the data set. And this gives me my set of cluster labels. Okay, so if I would like to create one of those silhouette bar plots that I saw when talking about the silhouette score, all that I need to do is basically use the following function here. So basically, unfortunately, scikit-learn does not have a function, automatically that will automatically create these silhouette plots. So you can basically just use this function that I'm defining here. Just copy paste that into your homework assignment. So you can use this function that I've created, And all you need to give it is the data set that you have just clustered, as well as the resulting cluster labels from the clustering that you've just created. And what this will do is create a silhouette plot for your resulting clustering. Okay. And so again, what this silhouette plot allows for us to do is not just evaluate the cohesion and separation of each of the individual points in the clustering, but can also give us a sense as to how cohesive and well separated each of the individual clusters are. So for instance, what this tells me is that cluster 2, and generally speaking, cluster 1, tend to be much more cohesive and well separated than cluster 0, because on average, their corresponding observation silhouette scores are a lot higher. And furthermore, we're seeing, much more of this dramatic drop-off happening with cluster 0. The best case scenario would be, you have these clusters that are much more well-rounded, suggesting that, all of the observations have relatively the same amount of cohesion and separation. But what we're seeing here is this much more dramatic cutoff, number 1, within cluster 0. And furthermore, we're also seeing, there's a few observations assigned to cluster 0 that have negative silhouette scores. So again, what this means is that there's actually some observations assigned to cluster 0 that are actually closer to either cluster 1 or cluster 2. We don't know which cluster it is, but we know that there are some observations that are actually closer to some other cluster rather than the one that it was actually assigned to. This tells us that cluster 0 has the worst cohesion and separation. Okay. All right. Any questions on that? Okay. And if we, for instance, want to find the silhouette score for each individual point, now the nice thing is there is actually a scikit-learn function for that. So we can use the silhouette samples function. And so we can give it our data set that we've just clustered, as well as the corresponding cluster labels of the clustering. So what that does is it creates a corresponding set of silhouette scores for each point. And for instance, if I wanted to, get a sense as to what those silhouette scores might look like, if I, for instance, wanted to sort them, I can take my data frame, which I have added. Ugh. All right. Oh, that's annoying. I can take my data frame in which I've added this silhouette scores column to it, and I can use the sort values function to sort the corresponding rows by the silhouette score. And so for instance, I can see that the observation with the most cohesion and separation is this one that has a silhouette score of 0.639. And we can actually see, there are some observations in the clustering that actually have a negative silhouette score, suggesting that they are much closer to some other cluster than the one they were assigned to. Okay. And finally, we could simply just take the average of like all of these points ourselves, but if we wanted scikit-learn to just quickly do that for us, we can simply just use the silhouette score function and give it the data set that we have just clustered, along with the corresponding cluster labels. And what that tells us is that, our clustering of this particular data set had an average silhouette score of 0.43. So what that roughly means is that, generally speaking, points within a given cluster are basically about half as close or twice as close to each other, or to the points in the cluster that was assigned to, than points in some other cluster, the nearest cluster, if you will. Okay, so that suggests a decent amount of cohesion and separation of the given clustering that we found. Okay, any questions on that? Okay. And so if we want to, not simply just perform this k-means cluster analysis in a very naive way, we could use the k-means elbow plot. So we've seen this code before. Okay. Now, it's not quite obvious what, it's not immediately obvious what the elbow is in this plot, but I would say I see suggestions of significant amounts of leveling off happening at, maybe k equals 4, perhaps maybe even k equals 8. So it's a little bit unclear. So if you're ever unclear as to what the k-means elbow plot is suggesting, you might try clustering the data set into, multiple cluster rings and seeing if you can find additional insights, for instance, as to A, maybe which one is best, or B, perhaps it might be the case that, for instance, we do in fact have 4 clusters, but it could be the case that there might actually be sort of like this sub-cluster relationship in which these 4 clusters might actually break down furthermore, maybe into 8. So this is something that you would want to explore. Okay, but unfortunately we saw that the k-means elbow plot is a k-means dependent evaluation metric. So it's only, the k-means elbow plot is only able to detect the number of clusters that k-means itself is able to detect. So we might instead suggest referencing a average silhouette score plot to furthermore examine how many clusters the given clustering might have, or basically what is the most effective number of clusters to look for. So basically the way to generate an average silhouette score plot, the code is almost exactly the same as to how you would do that for a k-means elbow plot. The only real difference is that you are, rather than calculating the inertia of a given k-means clustering, now you're calculating the average silhouette score. So you put all those values into a plot. And so what we can see here is that when we're choosing the best number of clusters to look for based on an average silhouette score plot, as opposed to the elbow plot method, we're now looking for the cluster number that produces the highest average silhouette score. So this might be the clustering with 8 clusters or the clustering with 10 clusters. So they look pretty close to each other. So given the fact that the k-means elbow plot also was validating that perhaps there are 8 clusters in the data set, I might choose to focus more on this k equals 8 cluster number as opposed to this k equals 10 cluster number. But again, for a more thorough analysis, you might explore both clusterings, both 4, 8, and 10, and see what kind of different insights you might unlock. Okay. So based on my suggestions of the elbow plot method and the average silhouette score plot method, I might look at 2 new clusterings. I might look at k-means, in which I'm looking for 4 clusters. And so that creates this corresponding silhouette bar plot. Okay. And so we can see the average silhouette score when we used 4 clusters is in fact a little bit higher than when we were using 3 clusters. We can see that further validated in each of these 4, cluster silhouettes, if you will. So we can see that on average, these silhouettes are higher, but it does look like, for instance, cluster 3 has the worst cohesion and separation because, on average, these points are a lot lower. And for instance, we also see that, cluster 3 and cluster 1 also happen to have these points with negative silhouette score values, which indicates that there are a few points that are in fact closer to some other cluster than the cluster that they were actually assigned to. Okay. And yeah, quickly running out of time here. And for good measure, we might also explore what the average silhouette score was suggesting. So the clustering that produces the highest average silhouette score was basically the one with 8 clusters. So we might examine that corresponding silhouette plot. And we can see that we are getting an average silhouette score that is even higher. And we can see that suggested in many of these cluster silhouettes. So these, many of these cluster silhouettes are actually starting to get pretty close to 1. We can see that this comes at the expense of, some clusters here, like this one here, which do look like they tend to have lower average silhouette scores, suggesting that, cluster 0 and cluster 4, for instance, do not tend to be as cohesive or well separated, if you will. Okay. So yeah, so basically this, what we just discussed here are some ways that we might go about evaluating how good a given clustering, is when it comes to, identifying the clusters that we're actually looking for. So again, what we are evaluating is simply how cohesive and well separated is the given clustering of the given data set. But again, you want to take this average silhouette score with a bit of a grain of salt. Because again, if you're dealing, for instance, with a non-well separated data set, then it's very unrealistic to expect that any of your clustering results will give you that high average silhouette score. So something to keep in mind. Okay, so any questions on that? Okay. I'm quickly running out of time, so yikes. I feel like I go slower every semester that I teach this class, and I don't know why. Shoot. Okay, so one thing that I would like to quickly go over is another type of clustering evaluation metric. So we call these types of clustering evaluation metrics supervised clustering evaluation metrics, because it involves incorporating some additional set of pre-assigned class labels that we would like to essentially add on to our analysis after we have already clustered our original data set that we're focusing on. So for instance, the overarching research question that I would like to answer with this data set is there an association between the, let's just say, 4 k-means cluster labels that I have found for this data set and my set of pre-assigned class labels. So whether or not the auction was normal or abnormal. So given that the cluster label that we assign with k-means actually really doesn't matter, what that means is that the task of evaluating whether to cluster rings or whether a cluster ring and maybe a set of pre-assigned class labels is the same is not necessarily going to be as simple of a task of simply just subtracting like the 2 sets of cluster or class labels, or simply just saying, is this label the same as this label? So for instance, let's just say I've clustered this data set of 6 observations into 2 clusterings that we see labeled as such here. So the question is, setting up a poll, are these 2 clusterings the same? Okay, I'm kind of running out of time, so I'm just going to shut the poll down now. Okay, so yeah, we do see that this majority of folks say that this is in fact the same clustering of the same data set. And that is correct. So basically what all this is really telling us is that because objects 1, 2, and 3 all have the same cluster label, what that means is 1, 2, and 3 all belong together. 4, because it has a distinct cluster label, than any other point in the data set, what that is telling us is that 4 is by itself. And because 5 and 6 also have a distinct cluster label, it's telling us that 5 and 6 are together in a cluster. So yes, this is in fact the same clustering of the same data set. So given that the labels assigned to a clustering don't actually matter, what we actually want to be thinking about, and I'll stop here, when evaluating if, or essentially how similar a clustering is from another clustering, or for instance, how similar a clustering is from a set of pre-assigned class labels. Rather, what we want to be looking at is and comparing is the number of agreements between the two clusterings, the number of pairwise agreements between the two clusterings, and the number of pairwise disagreements between the two clusterings. Okay, so I've gone over time, so I will stop there. So something I do want to say, unfortunately, in order to, create the homework assignment in such a way that, doesn't require like a whole lot of overhaul, or in other words, to keep using really effective, interesting homework assignments, I do actually need to go through like a few more minutes of content, probably no more than 7 minutes. So unfortunately, what I'm going to have to do is I will, after class, film about 7 more minutes of content, which will be, essentially required in order to get through the next homework assignment. I find that I go a little bit slower in the first few weeks, but I don't think this will, generally speaking, be a problem. So yeah, be on the lookout for that additional video content. I will send an email basically telling you when it's ready. But yeah, other than that, yeah, we will wrap there. I will stop recording.